to this lecture series on noise control in mechanical systems with me, Professor Sneha Singh from IIT Roorkee. So, we have discussed about some noise control strategies. So, we started discussing about acoustic metamaterials as one of the materials used for sound absorption and sound wave manipulation, and then in that we studied about space coiling metamaterials, what was the working principle of these metamaterials and how they can be used to redirect and control the sound waves and how they can achieve attenuation of these sound waves. Today we will start with this another kind of metamaterial called as the sonic crystals, and that is what we will be discussing in today's lecture. What are sonic crystals? What are the classifications of sonic crystals, and then we will discuss about the working principle of these sonic crystals, and then this topic will continue forward in the subsequent lectures as well. So, what are sonic crystals? Let us just start with the word crystal. Okay? You can see a crystalline kind of a structure here, and if you have studied about solid state physics, or if you have studied even in the 10th and the 12th class about crystalline, you know that these solids, they can exist as crystalline form or they can exist as amorphous form. Okay? So, what is this crystalline form? What is the name crystal in general for a solid material? It means that a material or a solid material where its building block, it could either be its molecules or it could be its atoms, but whatever is making up that solid material, that is arranged in a highly ordered microscopic structure that forms a regular lattice. Okay? For example, you have the rock salt or NaCl, it is a crystalline structure, the Na molecules and the Cl molecules over here, they are arranged periodically in various kind of lattice structures. You have the face centered cubic structure, you have the body centered cubic structure, you have the cubic lattice and so on. So, let us say for example, something like this, Na plus Cl minus arranged periodically in some kind of an array. And in a 3D format, you can have these kind of molecules arranged to form various kind of cubic arrangements, face centered arrangements, body centered arrangements and so on, and it continues in the 3D, this arrangement of the molecules. And due to this, the materials, they have shiny appearance and they have sharp edges like that. So, that is the concept of a crystal where the element or the molecule is existing as a highly ordered set in the 3 dimensions. This ordered kind of matrix that you can see is called as the lattice. Okay? It is the periodic, this kind of a ordered periodic layout of the molecules, that is called as its lattice. So, sonic crystal is what? It is some kind of periodic structure. So, you might have guessed that it might be some kind of a crystalline structure that can be used to control sound waves. So, it is very similar. So, what is it? It is one of the first acoustic metamaterials that was invented and studied, and it was found to control the propagation of the sound waves. So, the study of acoustic metamaterials, you can say, very closely coincides with the invention and the formulation of the concept of sonic crystals. And this concept is derived from photonic crystal, which is a crystalline structure or a periodic arrangement of material used to control the electromagnetic waves. So, what is a sonic crystal? Let us now straight away come to the definition. It is an artificial crystal made of a finite size of highly ordered periodic array composed of sonic scatterers embedded in a homogeneous host medium. What is a sonic scatterer here? Let us see these terminologies. It is any kind of dense sound reflecting material. So, usually in the sonic crystal, the host medium is some kind of fluid acoustic medium. It could be air or water or some kind of a light fluid, and the scatterer is any kind of solid structure. It could have any kind of shape, and the property is that the impedance of that should be much higher than the host medium. So, it acts as a acoustically rigid kind of a structure to scatter the waves. Okay. So, it could be metals, hardwood, etc. So, let us see schematically, for example, let us take this definition here. It is a artificial crystalline kind of a structure made by a finite size of highly ordered periodic array composed of sonic scatterers in a homogeneous host fluid acoustic medium. So, for example, let us say our host medium is air, which is the most common acoustic medium, air. So, in the air, if you could just put cylinders, some acrylic cylinders in the air and arrange them periodically. So, with a constant gap. So, I am arranging these cylinders periodically in the 2D layout I am making of them, okay, and maintaining constant gap. So, some kind of lattice arrangement I am creating. So, here my building block is this acrylic cylinder which is arranged in a 2D periodic format, okay, and at a fixed periodicity or in a regular ordered arrangement in the air medium. So, this also is like a crystal, because here the scatterer is behaving like the molecule of the crystal, which is arranged in a ordered layout within the host medium. So, or you can have some other examples could be steel plates. So, we can have large plates of steel arranged periodically in the air and so on. So, all of these kind of dense structures are arranged periodically in some acoustic medium or in a ordered lattice format in an acoustic medium. They can be called as a sonic crystal. So, what is the classification? So, you know that first of all sonic crystals, they are used for attenuating the sound and for bending the sound waves. And based on, because here what is happening, you can boil down a sonic crystal to simply any kind of dense scattering material structure that is arranged in a ordered periodic layout in air or any kind of fluid medium. In the fluid medium we have some scattering structure and we are arranging it in a periodic layout. So, depending on what is this periodic layout or what is the direction of periodicity, the sonic crystals can be classified as 1D, 2D and 3D sonic crystals. So, let us see a 1D sonic crystal here. You can see this in this figure here. We have arranged the steel plates in air and we are maintaining a constant gap between two steel plates. Let us say the gap between this and this and this and this is some constant gap, and in an ordered fashion, not haphazardly but in an ordered fashion. Okay. So, the gap is maintained constant and we are arranging it. Okay. This is some constant gap, we can say gap we are maintaining between the steel plates. Then what you see is that here there is a periodic layout in only one direction. Okay. The periodicity is in this direction here, pointed given by this arrow. This gives you the direction of periodicity. So, what you observe here is that, let us say beta 1 and rho 1 are the bulk modulus and the mass density of the steel, and beta 2 and rho 2. So, this is let us say for the steel here, okay, or the scatterer, whatever scatterer you are using. In our case, for example, we are using steel, and this is for the, so this is for the scatterer and this is for the host. Okay. Then what you see is that if you observe it in this direction, periodically the beta 1 and rho 1 is changing. So, when the sound waves are propagating from here, okay, these sound waves, they are propagating from here. So, first they encounter a medium with a different beta 1 and rho 1, and then they encounter a new medium. So, first of all we have a medium with a particular beta 1 rho 1, and then we have another medium with a different beta 1 rho 1, and then we have the same medium again with a beta 1 rho 1, and then we have the airs. So, in that way periodically the beta 1 and rho 1, which is the bulk modulus and density, keeps varying periodically at a certain gap in this direction. In the 2D, now the same thing happens now in two different directions. So, for example, you have the solid cylinders, you can have the steel cylinders placed in the air. So, what you see is that, and they are placed in a 2D periodic layout. So, here the variation that is happening will be in two different directions. Okay. So, once again, if you have this as the property of the scatterer that you are using, and this is for the property of the host medium, they both have different bulk modulus and density. So, what you see is that if you take this as your two dimensions, okay, this and this, what you see is that when the sound wave is propagating, there is a change in these properties periodically in this direction. Okay. So, first they encounter the cylinder, they encounter the air medium, then again the sound waves will encounter the cylinder with a different rho, and then again they will encounter the air medium, and then they will again encounter the cylinder medium, and so on. So, the B rho keeps changing periodically over this direction because the cylinders are periodically placed in this particular direction. But the same thing happens here as well in the other independent direction. The sound waves here, this particular region has a particular beta rho, and periodically there is a variation, then a new beta rho for the air gap, then again this beta rho for this steel cylinder, then again the beta rho for the air gap, and then the beta rho for the, and so on. So, periodically in the two direction the properties keep changing. Okay. And in the 3D, well, you can have now the pairs of steel arranged in a 3D cuboidal fashion like this, and as you can see here in this direction the properties keep changing periodically. Okay. The air gap, so beta rho for the steel, the sound waves will encounter, then the beta rho for the air gap, then again the beta rho for the steel, and then again the beta rho for the air gap, and then the steel and air gap and so on. So, this is happening in this direction, and there is a periodic layout in the 3D. So, even here in this direction also periodically the properties keep changing when the sound waves are propagating. Okay. So, the red zone indicates the beta rho for the steel, and the yellow zone indicates the beta rho for the air medium, and so on. And in the same way here also you can have periodically changing these properties here, and here the direction of periodicity, they are independent of each other. Okay. So, three independent directions, and in the 2D and the 3D sonic crystals the periodicity may be different for the independent directions. It can be same also, or it can be different, like that. So, it can have the same periodicity, it can have a different periodicity, and so on. Okay. Now that we know that these are the three types of classifications, the most commonly studied solid crystals are sonic crystals are 2D and 3D kind of sonic crystal. Again, this shows a typical sonic crystal that was manufactured in our lab, one of the research studies where we had these hollow solid cylinders arranged in a 2D format. These are some of the common sonic crystal studies are 2D and 3D because they are able to better manipulate the sound waves, and once, and especially when you have independent, you are giving them two or more independent directions of periodicity, and especially if the periods you maintain as different, you get. So, that is the most commonly studied one because you are getting more unique properties and a better sound wave manipulation if you have different periods in the two different directions. Okay. So, different periods in the two different directions. So, out of the two, 2D and the 3D sonic crystals, the 2D is more easier to manufacture, not just easier to manufacture in terms of the scatterer, but it is also easier to install and arrange. Okay. So, the installation and the arrangement as well as the manufacturing is much easier for 2D, and hence they are the most widely studied kind of sonic crystals. Let us just see a few terminologies related to sonic crystals. So, now we have firstly the scatterer, which you already know. I will indicate it using some. So, let us say I am looking from the top and we have an arrangement of crystals in a 2D format. So, let us say steel cylinders arranged in an ordered 2D layout in air. Okay. And here the steel is indicated by this black ball. So, I am looking at the top, the layout of it, and the air is indicated by simply the white zone, or fine, I can, and the air could be represented by this kind of a dotted air medium. Then this is the the top view of the layout, and let us define the various terminologies within this. So, remember that this is a 2D crystal, so there will be two independent directions of periodicity and hence two different periodicity in the two directions. Okay. And so on, and the same cylinders arranged like this here, 2D layout. Okay. And so on in this direction as well, and we have the air medium surrounding them. So, this is the air medium over which they have been embedded, and this shows the top view of this structure. Now, let us define some terminologies related to this. Here our steel cylinder is the scatterer. Here this steel cylinder, which is given by this thing here, is your scatterer, okay, or the sonic scatterer also you can say, because it is. So, this is what, this is usually any kind of structure which has a high impedance compared to the host medium and can scatter the sound waves incident on it. So, if a sound wave is coming, typically when it is incident on it, most of it gets scattered, only a very small portion of it passes through. That is the definition of the scatterer. Okay. Is able to scatter, able to reflect or scatter most of the sound energy incident on it. Okay, that can scatter most of the sound energy incident on it. It can scatter or reflect back most of the energy. Transmission is very low. The transmission is very low for these scatterers. Okay. So, how can this be achieved? You can have a more higher acoustic impedance, much higher acoustic impedance of the scatterer compared to the host medium, then you would be able to get more reflections and scattering and very less transmission because of the higher difference in the acoustic medium. Okay. So, they are able to reflect or scatter most of the sound energy incident on them, and the sound transmission is very low through these scatterers. Okay. And here the host is what? This is the air medium. Here air medium itself is the host, and what it means, it is the acoustic medium with much lower impedance than the scatterer. Okay. So, it is that acoustic medium which is in the background where the scatterer is embedded in, and it has much lower the acoustic impedance than the scatterer. Okay. Now, let us see the periodicity. So, over here what you observe is that in this direction, so there let us see these two independent directions of periodicity. Okay. Let us call it some direction x and y. Then in the direction of x, what you observe is that there is a constant gap between the crystals, let us call it A1, and so on throughout, and in the direction of y there is a constant gap of A2. And so on. Okay. So, here periodicity in x direction is simply A1, okay, which shows how periodically it is changing. So, this is simply the spacing between the scatterers. Okay. Okay. So, this is simply what this is here A1, it can also be seen as the uniform spacing. In many of the recent research you have sonic crystals with irregular spacing or continuously varying spacings as well, but primarily in the very basic sonic crystal structure that was proposed, usually the periodicity was maintained constant in the direction. So, this is the uniform spacing measured between the centers of the two adjacent scatterers. Okay, a uniform spacing that was maintained between the centers of the two adjacent scatterers. Okay, we can also call it as a vector, just like in the crystal we have lattice vector. If suppose these are your x and y directions, we can assume a vector A1. Okay, there is a vector, this vector here, okay, A1, and then this vector here A2, the A1 and the A2 vector. Then here A1 can be called as the lattice vector. Okay, it is a primary lattice vector. Okay, vector has a magnitude and the direction. So, here it is a vector, what its magnitude is the periodicity in that direction is equal to the periodicity value in that periodicity value, and the direction of this lattice vector is the direction of the periodicity. Okay. In the same way, the periodicity in the y direction is simply A2, which is the uniform spacing this is for x direction, this is the uniform spacing between the centers of the two adjacent scatterers in the y direction or the other independent direction, and the vector corresponding to that A2 vector is another primary lattice vector. So, for 2D sonic crystal we will have two lattice vectors, two independent lattice vectors. For 3D we will have three independent lattice vectors, and for 1D we will just have one independent lattice vector. So, this is another primary lattice vector, and because it is a vector quantity, what it means is that whose magnitude is simply A2 or the periodicity. So, the magnitude of this A2 is the value of periodicity or the spacing, and the direction is gives the direction of the periodicity. Okay. So, these are some of the basic terminologies. These various terminologies, we have the lattice vectors or the primary lattice vectors, then the periodicity values, and then the scatterer and the host. These are some of the basic terminologies, and I have explained using an example of steel cylinders arranged in a 2D layout in air, what do they mean. Now, let us see, because when I discuss about the working principle, these terminologies might be used. So, I sort of incorporated that. So, the working principle of sonic crystal can be defined, there are 4 working principles you can say. The first is multiple reflections and scatterings that happen while the sound wave is propagating. Then you have the wave spectral gap that results, or the band gaps that result due to the periodic variation in the elastic properties, and the theoretical underpinning of this kind of phenomenon is the Bloch's theorem. Then we have the local resonance that leads to various kind of negative elastic properties. Then we have some constructive and destructive interference that happens because of the periodic lattice itself, and here again the theory is based on the Bragg's law of refraction. Okay. So, we will study them. So, in this class we will just study the first 2, and then in the next lecture we will continue our discussion on the next 2 kind of working principle. So, firstly, multiple reflections and scatterings. Obviously, scatterer is what? It is a medium of much higher impedance compared to the host medium. So, the name itself says a scatterer. So, which means that when a sound wave is incident on it while passing through the host, most of it gets reflected or scattered away, and this transmission is low. Okay. The reflection is high, the transmission is much low, and the higher is the difference between the acoustic impedance of the 2 media, the more will be this reflection and scattering that will happen. But here we do not have just one scatterer that is leading to the reflection and the scattering. If you think about it, here in this case, suppose some sound wave is propagating, it will first get scattered through the first layer and a small portion passes through. Then again there is some scattering and a very small portion passes through. Then again this one has some scattering, and then as the the layouts continue, the more and more wave is getting scattered, and this is leading to the attenuation of the sound wave. So, by the first layer a certain portion of the energy is getting reflected back and the transmitted energy is lower, and when the second round of scattering happens through the second layer of the scatterers, then some more energy gets reflected back and even much lower transmitted energy passes through into the third layer of scatterers. Again this phenomenon continues, and by the time the sound wave has gone through periodically through several layers of scatterers, much at each layer reflection is happening, scattering is happening, and transmission is getting further reduced, and this happens multiple times, and due to this these multiple scatterings and multiple reflections happening at these multiple layers, it leads to an overall attenuation in the sound wave propagation. Okay. Then the second one is the wave spectral gap or the band gap in the sonic crystals, which is governed by the Bloch's theorem. Again the Bloch's theorem came first from solid state physics, but then this theorem was extended to the acoustics of the periodic structures such as a sonic crystal. And this theorem is valid for any kind of periodic structure, and by periodic structure in acoustics we mean a structure where the acoustic properties are varying periodically. What are the major acoustic properties? The major acoustic properties are beta and rho, or the bulk modulus and the mass density, and these are varying periodically. That will create a periodic structure, and in that kind of a structure Bloch's theorem will be valid. So, whenever we have any structure where there is a strong modulation or a strong periodic modulation or variation in the mass density or in the bulk modulus of the structure, or both, it can create some spectral gaps of frequency bands where wave propagation is forbidden. Okay, so that is essentially what happens, and for this to happen, the spatial modulation or the period by which the property is varying should be of the same as the wavelength in the spectral gap. So, suppose you want to control the sound waves of lambda wavelength, then the gap or the periodicity that you will have to maintain in the structure is same as the wavelength that needs to be controlled. Then what will happen is that those wavelengths will not pass through essentially, and they will be blocked, and the regions or the frequency which are getting blocked are also called as the frequency, the band gaps. So, let us see how this happens. Okay, why the periodic variation is stopping some sound waves to travel through, such that the sound waves that are getting stopped, they have the wavelength which is of the same order as the periodicity of these periodic structures. So, the Bloch's theorem states that when the acoustic field inside any periodic structure will have to take the same symmetry and the same periodicity as that of the structure itself. Okay? So, let us say waves that follow this Bloch's theorem are called as Bloch waves. So, let us say we have some periodic structure and a broadband sound wave was incident on these periodic structures. But once the sound wave is passing through, due to the Bloch's theorem, it says that once the sound waves are entering into this periodic structure, only those sound waves which have the same periodicity as the structure itself will not pass through this. So, the sound field inside this structure can only exist in this format, where they have the same periodicity as the crystal or the structure. And let us say we can represent the overall pressure field inside a sonic crystal using this formulation. So, here what we have, this is the overall acoustic pressure field, this is the periodic envelope. Okay. So, this is what this part takes same symmetry and the periodicity as the structure, it is given by this format. So, here the amplitude of the wave is varying periodically, the periodicity is the same as the lattice vector of the sonic crystal. So, suppose we are considering a sonic crystal that has got some periodicity of A, which means that the B and rho are changing after every A distance. Then the amplitude of the wave will also be periodic in nature and it will change with every A distance. Okay? And because it is a plane propagating wave, the nature of propagation will be maintained as a plane propagating wave, but the overall amplitude will be periodically varying with the periodicity of the structure. So, instead of having a simple constant amplitude into e to the power j k dot r, now we have a varying amplitude with a plane wave component. So, some of the properties when Bloch's theorem is solved in solid state physics, it leads to the Bloch waves having the following properties. Once again, the derivation of this is not within the course, but rather the Bloch theorem is a very extensive concept that you can study in physics and solid state physics, but for acoustics we are just taking the key conclusion points of the theorem and applying it to see how sonic crystals are behaving. So, the key concluding points of this theorem is that if the Bloch waves are existing in this periodic structure, they are quantized and they only exist as discrete orthogonal modes, and these are called as the Bloch modes. And these Bloch modes, they must have the same periodicity as the periodic crystal itself. And the acoustic intensity of the lowest order mode, it should reside in the acoustically denser region, which means that the pressure maxima should happen in the medium of higher acoustic impedance. So, just keeping this in mind, let us start seeing one by one what happens. So, let us say we have this periodic sonic crystal structure. So, within this structure, the sound waves, they can only exist as waves having the same wavelength as A. So, very first thing is that only the sound waves where lambda is equal to A, that kind of sound waves only can exist within this structure. So, the overall field will always have lambda is equal to A. Let us say the first mode, this is one Bloch mode is this, and this is another Bloch mode, and when you are going from a lower mode to a higher energy mode, then the higher energy mode has a pressure maxima in a more lighter medium. So, this is higher energy mode, it is having a pressure maxima in the air, whereas the lower mode is having the pressure maxima in the denser region. So, from the properties of the Bloch wave, we know that the waves inside this periodic structure or the sound field must maintain the same periodicity as the periodicity of the structure in itself. So, which means that the wavelength, the spatial periodicity of a sound wave is what? It is wavelength. Okay. The temporal periodicity is the frequency. Okay. With time, the periodicity of the wave is called as the frequency, whereas with space, the distance over which the wave is repeating its pattern, that is the wavelength. Okay. This is what? Wavelength is what? It is the spatial distance over which the wave is repeating its pattern. So, basically by definition the lambda itself is the spatial periodicity in the waves, okay. And the Bloch's theorem says that the spatial periodicity of the Bloch waves must be same as the structure's periodicity. So, that means that if suppose sound waves are passing through a sonic crystal of where the spacing is a in between the scatterers, then the lambda also should be same as a, d plus s, okay. The lambda should be same as the periodicity of the structure, and so the lambda of the structure is same. K is what? 2 pi by lambda. So, this means that k1 and k2, the k vectors is going to be same, and the lambda is going to be the same as the structure itself. Now, these are the two modes. Now, because mode 1 is residing in a denser zone and mode 2 is residing, the pressure maxima of it is residing in a lighter zone, which means that the two modes, they have different energies, where mode 2 has a higher energy than mode 1. Again, let me refer back to this, to the property, third property. So, by this third property, if suppose two modes have different energies, then their pressure maxima happens at the different regions. Whenever their energies are different, the pressure maxima or the peaks, okay, the crests and the troughs, they happen in the different spatial regions. More acoustically denser region happens for a lower mode. So, here as you can see by the nature of this, the mode 2 is higher because here the pressure maxima is happening in a lighter region, and in the mode 2 the pressure maxima is happening in a lower region. So, these two modes have the different acoustic intensity, and you know that acoustic intensity is what? It is for a plane wave propagation, it is p square by rho c, okay, the square of the pressure divided by the characteristic impedance. In the acoustic fundamentals we have seen this derivation. So, this means that the P RMS 1 whole square by rho 1 C1 for the first mode should not be same as the P RMS 2 whole square by rho 2 C2 for the second mode, okay, because I is P RMS whole square by rho C for a plane wave. So, that is why this should not be the same, and hence in that, but we know that both waves, they have the same waveform, the RMS pressure is the same, and because if you consider not a small region but a much larger region of the sonic crystal, then overall for a much larger region of the sonic crystal you have the same number of scatterers, the same amount of air medium. So, the overall density for both the modes is going to be the same. So, the only conclusion that we can draw is that if P is the same, rho is the same, then the C must be different for the two modes, or the speed of sound must be different, which means that lambda 1 F1 should not be equal to lambda 2 F2, but we know that lambda 1 is equal to lambda 2 by Bloch's theorem. So, that means that the frequencies must be different for the two modes. Thus, in a periodic crystal arrangement, by the Bloch's theorem we see that the sound waves only exist as these Bloch modes, these discrete Bloch modes, each of which have a different frequency. So, they have different frequency. So, only some discrete frequency points are there where the waves are existing. All the other frequency the wave cannot exist, which creates some gaps, and these gaps where the waves cannot exist are called as the band gaps. Okay? So, not all frequencies can exist, only a certain quantized discrete frequencies can exist, and all the in between frequencies where the wave cannot exist in this structure, they are the band gaps of the structure. So, with this I would like to close this lecture. Thank you for listening.